Good morning, everybody. Welcome to Honors Chemistry. Today is Wednesday, May 13th, 2020, and today we're going to be discussing rate laws and how they apply to kinetics. So let's go over and start by taking a look at the agenda so we can see what to expect for the week. And this is, here we go. All right, so yesterday you watched this kinetics video, and I'm going to talk a little bit about that today, just go over the questions in the Google form, make sure we all agree on what you should have witnessed. And then you watched two Mr. Anderson videos yesterday, and he actually made an error in one of the videos. I don't know if you caught it, but we're going to talk about the two examples he did in the rate laws video, and we'll discuss Mr. Anderson's error and why he was in error. He doesn't normally do that, but it's a good teaching point. I have some notes for you today, the rate laws notes. They're via PowerPoint, and I would recommend that you have your brain books ready so that you can write them down, and then next year when you take varsity chemistry or when you enroll in chemistry in college, then you'll have some notes that will help you through your next chemistry class, wherever that is. So I would recommend getting your brain books at the ready as well. Sorry, I forgot to put that in here, but we are going to be taking some notes today, and I'm going to try to fly through those notes as quickly as I can so that we can get to some practice problems. Okay, we'll look at those practice problems that Mr. Anderson did and understand his error. And then there's a worksheet that's up on Google Classroom that I'd like you to print or at least just have access to during this period. And your homework will be to complete that worksheet. So we'll get you started on it during class, and then we'll go from there. You guys can try to finish up anything else from homework, okay? Tomorrow, I'm gonna have you guys start designing an experiment, okay? I like to have you guys doing hands-on chemistry as much as possible. And if we were in class, I would have you had you do the glow stick experiment in class. And the other thing I would have had you do was then design a multivariable experiment for how to increase the rate of the reaction with Alka-Seltzer in water. And the reason why I'm telling you about this today is because I want to give you an opportunity to get Alka-Seltzer. So you don't have to actually perform the lab. Okay, I know some people are very wary of leaving their houses, of going to grocery stores, of ordering things from outside sources and getting packages on their doorstep. So you absolutely do not have to perform the lab. I'm offering you extra credit if you do, however. Okay, so everybody's going to design the lab. Everybody's going to design an experiment that's a multivariable experiment that determines the fastest way to get an Alka-Seltzer tablet to dissolve in water. Okay, so if you think back to the 5 ways to increase the rate of a chemical reaction, right? Remember we watched that video, the TED Ed video last week on 5 ways to speed up a chemical reaction and get a date, right? You can increase the temperature, you can lower the volume of the reaction container, but again, lowering volume only affects things that are in the reactants that are in the gaseous phase. You can add a catalyst, you can increase the surface area of the reactants if they're in the solid state. Let's see, what am I missing? Temperature, volume, catalyst, surface area. Uh-oh, what am I missing? Oh, concentration. You can increase the concentration of one of your reactants, okay? And so I want you to think back to those 5 ways of how to increase the rate of a chemical reaction. And I'm gonna ask you to choose 2 of them that you think you could control in a scientific experiment to maximize the rate by which an Alka-Seltzer tablet dissolves in water, okay? And you're gonna have to design your own experiment, meaning you're gonna have to make a list of materials, you're gonna have to write your own protocol for how you would do this. Now, everybody's going to design the experiment, and I'll show you, I've been working on this a little bit this morning. I'll post it up a little later today, but essentially there's gonna be a document, a Google document that I'll share on Google Classroom, and I'll make it an assignment. And it'll mimic the labs that we normally do. So there will be a purpose, the background knowledge. I'll ask you to do a couple background knowledge questions. I'll ask you to make a list of materials. I'll ask you to write a protocol. I'll ask you to include any safety precautions. And then I just want you to have a data table, okay? So everybody's gonna do these sections, if you will. Now, the extra credit comes in is if you actually perform the lab. Okay, so you have 5 days to get your hands on some Alka-Seltzer tablets if you want. I don't want you to do something that makes you feel unsafe or makes your family feel unsafe going to the store for this, okay? But if you want, or maybe you have Alka-Seltzer tablets at home, you have what, today's Wednesday, Thursday, Friday, Saturday, Sunday. You have 5 days to perform the lab. And get all the materials you need. And, you know, with Amazon Prime, that should hopefully not be a problem. Anyway, you actually perform the experiment, collect some data, and then write up a conclusion. And I will go ahead and give you guys some extra credit. But I'm trying to think, how am I going to keep these students from just copying data or making up their own data? And so in order to get the extra credit, you'll have to complete the data table and write your conclusion based on your data. But also, I'm going to ask that you make a short explainer video about what you did to maximize the Alka-Seltzer reaction and post it up on our Instagram, okay? And so that way I'll see you performing the lab, I'll know you're doing it, and that'll be worth extra credit. Again, you don't have to do it, it's just extra credit. Okay, so that is due on Monday at 8 a.m. And the reason why I like to have you guys do things on Monday at 8 a.m. is because that gives me all day on Monday to actually catch up on grading. That's what I've been using Mondays for at this point, is just catching up on grading. Okay, and then I'll post up another practice worksheet for you guys to do on Google Classroom. We'll meet back up on Friday and we'll review anything else that you might have questions on. And then that's pretty much it for kinetics. I'm realizing our time left together this year is pretty short. I still have to get through equilibrium and thermodynamics and acids and bases. And so, and maybe a little bit of redox, we'll see. So I'm gonna move on from kinetics. I might give you a short little quizam, something little. Next week we'll take a look and see you know what we can do, but I'll go ahead and give you guys probably review some stuff tomorrow, and then might just give you that short little quizam on Tuesday. Okay, and then we'll move on. Next week our next unit is going to be equilibrium. So if you have any questions, feel free to speak up, or you can wait until the very end if you don't want to be recorded. But that's what we're looking at for the week. Okay, and again, your Instagram extra credit opportunity is listed right up here. It doesn't need to be a long video. Just show me what you did and how you maximized the rate. And again, it's multivariable, so you're gonna have to choose more than one of those 5 ways to increase the rate of a chemical reaction. Okay. All right, what else? Don't forget to go in and check in on the attendance sheet today if you haven't done so already, okay? And I think that's it. So let's go ahead and start with our molecule of the week. Do I have some more people in here? Oh, there we go. All right. Okay, I know we are in the middle of AP testing. And I don't know if any of you have taken an AP test yet this week, but they are quite different. And I'm seeing all kinds of different comments about them. But my students take their AP chemistry test tomorrow, and after I talk to them, then I'll know some more about it. But anyway, molecule of the week this week is based on the fact that there's a lot of stressed out students. And so I've chosen norepinephrine. Norepinephrine is both a hormone and it's a neurotransmitter. So hormones are released into the bloodstream and neurotransmitters are released in the nervous system to communicate between neurons in the synapse. The hormone is released from your adrenal gland. The neurotransmitter is released from both your central nervous system and what's called your sympathetic nervous system. Your sympathetic nervous system is what is making you feel stressed, what's making you feel like when your heart starts beating really fast right before a test and you get nervous. Uh-oh, someone is not muted. There we go. Oh, I got more people joining. Here we go. There we go. Sorry, let's go back to that. So sympathetic nervous system is your nervous system, your fight or flight nervous system. It's the one that makes you feel stressed out right before a test, that excitement. And the idea behind the sympathetic nervous system is that it gives blood, it shunts blood to areas where you need it to survive. So it'll shunt blood to your eyes, it'll shunt blood to your skeletal muscles. So, you know, back in our caveman days when we would have to decide whether we would fight if we were in a stressful situation or flight, run away, right? It would provide our body the best chance of survival, right? Are you going to run from a bear or are you going to fight that bear, right? So it shunts blood to skeletal muscles. It dilates the eyes. It increases your heart rate to pump blood more efficiently. It's going to shunt blood away from your digestive tract. You don't want to worry about having to use the bathroom if you're in a life or death situation, right? And so those are all responses of the sympathetic nervous system, physiological responses of the sympathetic nervous system because of this molecule, norepinephrine. And when, let's see, this is what makes your hand shake, your heart pound. In medicine, it's used to treat what's called bradycardia, which is something you'll hear if you listen to those medical shows. It means slow heartbeat. So they can give a norepinephrine injection that'll make the heart beat faster to help maintain blood pressure. If people have low levels of norepinephrine or if it's improperly regulated in the body, it can lead to anxiety disorders, depression, blood pressure irregularities, or other health problems. And then there's different scientists call this molecule different things. So norepinephrine is the same thing as noradrenaline. As a matter of fact, epinephrine and adrenaline, they're two words for the same thing. Okay, so epinephrine and adrenaline mean the same thing. Norepinephrine and noradrenaline mean the same thing. The only difference between the molecule epinephrine and norepinephrine is one single methyl group, a CH3 molecule, a CH3 group that's sticking off of this molecule. I can't remember exactly where it is, but somewhere on there. Okay, so anyway, there's your molecule of the week. Okay, and when you start feeling that sympathetic nervous response, then you'll know it's norepinephrine that's responsible for that. Okay. All right, our next plan of action today then is to go over this Google form that I asked you to fill out. Actually, I'm not sharing right now, sorry. Let's go back. I just want to quickly go over the answers to the Google form that I asked you to fill out yesterday. Make sure that you don't have any questions and that we're all on the same page for what I was expecting of you there. So first one, in the little video you watched that was put forth by Flynn Scientific, you saw that there was a graduated cylinder that had oil on the top and water on the bottom. And it says, why does oil float on the top of water? It's a density thing, right? If something is floating or sinking, it's always density that is at play. So oil is less dense than water. Why does the sodium piece sink to the bottom of the oil? Well, because the sodium is more dense than the oil, so it sinks down through the oil layer. True or false, sodium metal reacts with oil? That's false, right? You saw the sodium sink through and it didn't react at all with the oil. But then when it got to the water, it started reacting, right? And sodium and water react very violently together. That's why it's kind of nice to do this reaction, because it's a safe way to do the reaction with the oil on top. The reaction doesn't turn into a very violent reaction. There's been stories, and actually even teachers at Costa, who take pieces of sodium metal and they'll take their whole class out to the pool and toss the sodium metal into the pool. And there's a boom, there's a big explosion that can be heard across campus when they do that. There's been situations though where chemistry teachers have injured their students doing this, not at Costa, but other in other situations around, you know, the United States that have happened. And so I don't do this with my students because I would never want to put you all in harm's way. But sodium does react very violently with water. And you can probably find some videos of people throwing sodium in a pool online if you wanted to. Anyway, the reaction creates something called sodium hydroxide, and hydrogen gas are the results. And so sodium hydroxide is an example of a base. We haven't gotten into acid-base reactions yet, but what they had done was they put something in that container called phenolphthalein, which is an acid-base indicator. And when there's a base present, the phenolphthalein turns pink. And so you probably noticed that there was a tinge of pink in the container after the sodium metal was reacting. And that was indicating that there was some sort of a molecule that's being produced. In this case, it's a base that was being produced to make that solution pink. Now that was a little bit beyond the scope of what your knowledge of chemistry is at this point. So I wasn't really expecting you guys to get there, but maybe you could have done it. So based on what you know about kinetics and reaction rates, speculate why the rusting reaction between iron and oxygen proceeds so slowly. What I was hoping you would get at here was that there was a very high activation energy for this reaction, okay? It takes, remember, molecules of oxygen in the air are always colliding with that iron, but because of the activation energy being so high, it's very few molecules that actually collide with the proper orientation and sufficient energy in order to get that rusting reaction to take place. So that's why it takes so slow. So fast reactions have a lower activation energy. Think about how a catalyst speeds up the reaction rate because it lowers the activation energy. So more collisions become successful collisions. If you have a really high activation energy, that means the collisions aren't as successful and they take longer. Okay. In a written chemical reaction, how does one indicate that a catalyst is used? It's written over the arrow. At the molecular level, describe how a catalyst functions, thinking collision theory. So a catalyst is not going to be able to increase the energy of the collision, right? They're not going to be able to make the molecules collide moving faster. That's temperature, right? A catalyst, what it does is it's like a matchmaker that brings the molecules together in the proper orientation, and then with the sufficient energy as well to overcome that barrier and make the reaction happen faster. Okay, so thinking collision theory, whenever I'm asking you about reaction rates, I want you to go straight to collisions to explain your results. Does it increase the energy of the collision? Does it increase the likelihood that the molecules are going to be oriented properly somehow? That's what a catalyst does, is it really increases the orientation factor. Okay, and so that's what I was looking at there. Hopefully you were able to get most of that from the video. Okay, next up, let's take a look at those rate laws notes. Now, I've uploaded these up onto Google Classroom for you already. They're right here. It says rate laws notes. So you can go back and look at them yourself, or you can just take notes while we're in class today. It'll give you something less to do tomorrow. And then later on, towards the end of the period, we'll look at this worksheet, and the answer key is already listed there for you too. So let's go to those notes. And to be honest with you, the notes are they're just heavy with information so that we can get through it and do some practice problems. I didn't try to make it too flowery with lots of fun, exciting stuff there. So let's see here. I'm just going to try to fly through them as quickly as possible. So you have the information at your fingertips and you know what it means, but we don't have to spend too much time on boring PowerPoint notes. Okay, that's my hope. So let's see here. Okay, hoping you can see what I'm seeing here. All right, so reaction rate laws. This is what you would put at the table of contents in your brain book. Reaction rate laws. Okay, so just a little to jog your memory here. You might think, what's the difference? Why is it that yogurt can be left out on the counter for 2 hours and before it goes bad, but it'll last for weeks in the refrigerator? Now think about that for a moment. If you leave yogurt out on the counter or in the trunk of your car after you go grocery shopping for just a couple hours, after just a couple hours, it goes bad. But in the refrigerator, it'll last for weeks. It's kinetics, right? Think about what's the difference. Well, the refrigerator is cold, right? And lowering the temperature of the reaction slows the reaction. So that spoiling process is a chemical reaction that you're slowing down by putting it in the refrigerator. It's inevitable that this yogurt is going to spoil, right? It will one day, but you can slow it down and make it last longer in the refrigerator because you're decreasing the temperature, and that's lowering the kinetic energy of molecules and therefore decreasing the likelihood that they are going to react and spoil. Okay, here's another one. What's the difference? Cookies can be baked on a car's dashboard. Did you know that? On a hot day, you can bake cookies on the dashboard of a car in 4 to 5 hours. But I could put them into my oven and bake them in 10 to 15 minutes. All right, again, this has to do with temperature, right? Obviously, even though our car's dashboard can get pretty darn hot into the hundreds, when you bake cookies in your oven, you're cooking them at 350, right? 375, something much higher. And so, again, it's a temperature issue. It happens faster in the oven because you're increasing the temperature of the reaction, increasing the kinetic energy of the molecules, and therefore increasing the energy of the collisions, right? Okay, next one. I know Mr. Anderson brought this one up in his video. What's the difference up in rusting? I don't know if he brought it up in this context, though. Up in the mountains, iron objects take a really long time to rust, but down at sea level, objects rust much faster. So let's think, what's the difference between up in the mountains and down at sea level, and what's required for this rusting reaction? Well, we have iron, right? At both places, iron is the same at sea level or in the mountains. But what's different is the concentration of oxygen gas in the air, right? Here at sea level, the concentration of oxygen gas is about 21% of our atmosphere. But as you move up higher into the mountains, the concentration of oxygen gas in the atmosphere gets less and less and less. And remember from our video that if you lower the concentration of a reactant, you decrease the likelihood of collisions. And if you decrease the likelihood of collisions, you're going to decrease the rate of the reaction, okay? And so that has to do with more of a concentration thing, okay? So there we go. All right, so here's where you can start taking some notes. So expressing reaction rate. So if I have some equation, A goes to B, the rate at which A forms can be expressed as a change in reactants with a change in time. And I already talked to you guys about this. I think I brought it up in terms of deli sandwiches, right? How we could look at how much bread and cheese was consumed to indicate how fast our reaction is happening, right? So if I take the final concentration of my reactant minus the initial concentration of reactant divided by the change in time, I'll get some rate, which is actually the tangent line, and we talked about that last week, okay? I don't know if I went a little too fast. You could also look at it in terms of, and by the way, this should actually be a negative value, because if A, I'm going to change this real quickly here. If A is a reactant, it's going to be used up, right? So that concentration is going to be decreasing, but rate is always a positive value. So by making this negative, it'll actually turn rate into a positive value. Okay, now we could also do the same thing. Let's see if I can do this real quick here in front of you. Except looking at B instead. And I know it's a little difficult to see because it's written on the colored part of this slide. But you could also look at the formation of product, right? So concentration of B2 minus the concentration of B initially divided by the change in time. So let's see if I can maybe, what do I do here? Make this a little bit smaller. That'll work. Okay, so there's another way you could describe rate. You could either look at it as how quickly the reactants are being used up or how quickly the products are being formed. That makes that a little bit more thorough now. Okay, all right, next. Expressing reaction rate. So since A is decreasing, its concentration is smaller than initially, so the delta A is negative, as I just stated. The negative sign is needed to make the rate positive, as all rates must be. So you can't have a rate happening backward, right? Rates are always going to be positive values. So the rate of disappearance of A is proportional to the concentration of A, such that, get this out of the way here. The change in it, it's a negative change over the change in time. And then this little sign here, this little alpha signal right here represents the proportional to. So the change in concentration of A over the change in time is going to be proportional to the concentration of A, okay? Or the rate of disappearance of A is proportional to the concentration. And what we're trying to say here is really that the rate is changing constantly throughout the course of a reaction. I'm going to stop sharing for just a moment here. If I were to, I'm going to draw this up on my whiteboard to make it a little bit more obvious. But if I were to look at the concentration of some reactant A here, remember brackets mean concentration of versus time. Okay, we said at the very beginning, the reaction proceeds really fast and then it slows down like this, right? And we said the rate at any point on this graph is the slope of the tangent line, right? So this is the slope here, the change in A over the change in time, right? But obviously that rate is going to be different at this point, and it's different at this point, right? So the change in A over the change in time here, the rate is going to be obviously a negative value, but it's a different slope here than it is here, right? So in other words, the rate is really, really fast at the beginning, and then the rate slows down as the reaction proceeds. And if you think back to that simulation I had you do, it makes sense because as the reaction proceeds, we're producing products, right? And so more molecules in the container are not reactant molecules, they're product molecules. So the collisions are not always going to be between reactants and reactants. They might be between a reactant and a product, or two product molecules instead. So the collisions are not always going to be between the right molecules, because now at this point in the reaction, right, if I were to look at this point of the reaction, you can see there's a lot more product molecules than there are reactant molecules. So the chances of two reactant molecules coming together, colliding with sufficient energy and proper orientation is much, much less, because the majority of the molecules in the container are products. So, my point being, the reaction rate changes throughout the course of the reaction. And the lower the concentration of A, the lower the rate, right? So whatever point or however much A is remaining will dictate the rate at that point. Generally, when we're talking about reaction rates, we talk about the rate after about 10 to 20% of the reaction is complete. So we're gonna talk about rate laws later on today, and generally those rates are measured when about 10 to 20% of the reaction is complete. So maybe right around here, this is what we would determine as the rate of the reaction. Okay. All right, let's see, I'll go back to that. Okay, So it's just proportional. The rate is proportional to how much A is remaining. That's what this side is trying to say. Uh-oh. Okay, so rate laws, this equation is called a rate law, and it's an expression for the rate of a reaction in terms of the concentration of reactants. In other words, the rate of a reaction is very dependent on the concentration of reactants, okay? However much, right, we just said that. Okay, so however much concentration of reactant is there is gonna affect the rate of the reaction. Okay, and again, you guys have access to these PowerPoints, so I'm gonna go a little faster, but you can always go back and look at them online. The rate constant, there's a rate constant that's called a K, lowercase k, for a reaction that's what's called a proportionality constant. It relates the concentrations of reactants to the rate of the reaction, right? And I'm gonna talk a little bit more about K in just a moment. The most important thing to remember about K is that it's only constant under constant conditions. Okay. The reason why is, remember how we said if you increase the temperature, you increase the rate. Well, how does it increase the rate in terms of a rate law? Well, because increasing the temperature increases this rate constant. So the rate constant is only constant at constant temperatures and constant pressures, constant conditions, okay? So the value, if the value of K is very large, it means that the rate proceeds very fast, the products form quickly. If the value of K is small, it means that the rate of the reaction is very slow, okay? All right, and then order of a reactant is the power to which a concentration or reactant might be raised to give the experimentally observed relationship between concentration and time. And Mr. Anderson talked to you guys a little bit about this, but it'll make a lot more sense when I show you some examples, okay? So the order of a reactant is just its power. And when we talk about reaction order with kinetics, you only have three choices. For the exponent, it's either 0, 1, or 2. Okay, the order of the reaction will be 0th order, 1st order, or 2nd order with respect to each reactant. Okay, and we'll talk about what that means. So here's what, for some reaction, if I have A plus B yields C plus D, the reactants have these coefficients in front. The little a refers to a coefficient to balance the equation. The little b would be a coefficient, okay? But the rate law for this reaction, we're saying that the rate is going to be dependent on the concentrations of reactants. It doesn't matter what the concentration of products are, the rate as it's proceeding is based on the concentration of reactant molecules, because those are the ones that collide to have to make the reaction happen. And then you've got this rate constant K that's only constant at constant conditions. And then you have these exponents, N and M. And N and M will be our orders, okay? So the exponents N and M in the rate law must be determined experimentally. This is really important. A lot of students think that you can just look at the chemical equation and just figure out the rate law. You can't. You actually have to figure out rate laws experimentally, and that's what I'm going to show you. The coefficients in the equation do not always correspond to the exponents in this rate law expression, okay? Just keep that in mind, because a lot of students have a misconception that you can just take this coefficient and put it here and this coefficient and put it here. That's not the way it works. It has to be determined experimentally, okay? All right, so reactant order. So let's say I have a rate law that looks like this, okay? And this one's a little silly because there's a 3 here. Again, your exponents will always be 0, 1, or 2, even in varsity chemistry. So this one has a 3. It does exist. You could have a 3, but for your purposes, you don't really need to know it. But anyway, I got these notes from Mrs. Hearn, so I'm using her notes, but so I didn't originally write these, disclaimer here. Anyway, so if you have this rate law expression, it's said to be 2nd order with respect to A and 3rd order with respect to B, okay? So the exponent is 2, we say it's 2nd order with respect to A, and because the exponent of B is 3, we say the reaction is 3rd order with respect to B, okay? Now, the overall reaction order is just adding up the exponents. Okay, so we say 2 plus 3 is 5. So the overall reaction order is 5, okay? All right, let's try another one. So the rate law determines the speed of a chemical reaction and is based on three things. One, the concentration of each of the reactants, right? Now you can see here, I mean, before you just memorize that concentration is one of the 5 things that increases the reaction rate. Now you can see, okay, yeah, if I increase the concentration of one of those reactants, A or B, it's going to increase the rate of the reaction. That's pretty obvious here, right? So the concentration or molarity of each of those reactants is going to affect the rate. And once again, remember brackets means concentration of, usually it's molarity, molar, okay? The exponent is also going to affect the rate of the reaction, right? Obviously, if this exponent is 0 versus a 1 versus a 2, that's going to affect the rate over here, right? And so the order will absolutely affect the reaction rate. And then also the value of K, this constant, is going to affect the reaction rate as well. So the conditions are going to affect the reaction rate. Okay, and so that's where a catalyst would come in, would be affecting K, or temperature would be affecting K, or changing the pressure or the volume of the container for a gas, that would affect K as well. All right. So factors that affect K, temperature and presence of a catalyst. So once again, K is a constant, but it's only constant at constant conditions. So it's a little bit misleading, but just if you remember that, you'll be in good shape. All right, and then this is probably a little bit past the scope of this class, but I'll just show you anyway. If you were to graph a 0 versus a first versus a second order reaction, in terms of the concentration of reactant over time, this is what it would look like. And I know a lot of you are mathematically minded, so I kept this in, but it's really more of a varsity level graph where basically with what you'll notice here is that with a 0 order reaction, it means that the concentration of A has no effect on the reaction rate. In other words, the slope is constant the entire time for a 0 order reaction. For a first order reaction, it's actually an exponential decay is what it's called, right? And so this is actually like a half-life would follow a first order reaction. That radioactive decay would follow first order kinetics. And then second order kinetics, you can see that rate is changing a lot more rapidly, right? Remember, the rate is like the tangent line. So you can see the rate changes much more rapidly with a second order reaction than it does with the other two. Okay. So a 0 order reaction basically means that the rate is independent of the concentration or the concentration of reactants. The slope of the line is constant and the reaction proceeds at the same regardless of the concentration. My best example for a 0 order reaction would be like a candle burning is the best example I've heard that you would be able to relate to. It doesn't matter whether I have this tiny candle that's like a little tea light candle or a big honking candle on my mantle, the rate at which that wax combusts is exactly the same, right? And so a 0 order reaction simply means that the rate of a reaction is totally independent of a concentration of that reactant. Okay. And this will, like I said, this will make a lot more sense when I show you some examples. Okay. The next type of reaction is a first order reaction. And this means the reaction rate slows down with time. So the line becomes less steep, you can see, with time. Okay. And it's yeah, that's pretty much it. And then the second order reaction means that the rate is even more sensitive to the reactant concentration. Okay. All right, and then here would be another way of looking at if we put rate on the y-axis instead and the concentration on the x-axis. You can see, again, the reaction rate is constant here. The rate for a 0 order reaction is totally independent of the concentration, okay? The first order kinetics would be a linear, 0 order is up here. This is constant, right? It doesn't matter. The rate stays the same the entire time. Okay, so 0 order, the concentration of reactant has no effect on the rate. The first order, you can see that the rate is linear, has a linear, the reaction rate has a linear relationship with the concentration. So as you increase the concentration, you can increase the rate. And it's a directly proportional relationship. And then second order reaction is more exponential, right? You can see that as you increase the concentration, that rate of reaction rises a lot faster. Okay, so I actually like this graph a little bit better personally. I think it kind of sums everything up a little bit better. Okay, now that's it for our notes. Okay, and let's see, how are we doing on time? Ooh. Oh, good. We still have a few minutes. Okay, so now I'd like to go over and look at the examples that Mr. Anderson did with you. He did 2 examples, and I'm going to start by showing you the example that was correct, which happened to be the second one he did. Let's see here. See if I can pull it up for you. Okay. All right, so this is the second example that you saw in Mr. Anderson's video yesterday. And this is the one that he did correctly, okay? So when we are trying to figure out a rate law for a chemical reaction, we're gonna have to have some experimental data to do it. You can't just look at a chemical equation and figure out the rate, okay? You have to have some experimental data. Okay, and so what you can see here is we have 3 experiments, and this is the kind of mentality you're going to have to employ to do your Alka-Seltzer lab also. So if I have 3 experiments here, these are 3 different trials, okay, and then they're showing me the concentration of each reactant that is in each trial. So in the first experiment, I used 0.1 molar of each reactant and measured the rate. Again, remember that rate is measured about 10 to 20% after about 10 to 20% of the reaction is complete, okay, or 10 to 20% of the reactant molecules have been used up. And I'll explain how we actually do this in the lab. In varsity chemistry, you'll get to do this, hopefully if we're back at school. But if not, I'll show you how we can measure the concentration over time, okay? Anyway, so we have a 0.1 molar, and then we measured the rate. And then second experiment, we changed the concentration of B. We doubled the concentration of B, as you can see, and then we measured the rate. And then the third experiment, we doubled the concentration of A and then measured the rate, okay? And so what we want to do to figure out the reaction rate law is we want to choose, first you got to figure out what the order is with respect to each individual reactant. I'm going to say that again. We have to figure out the order with respect to each individual reactant. And so in order to do that, we have to have only one variable. Okay. Remember, when we have good experimental design, you only want one variable. And so everything else has to be held constant. Okay. So here, I'll try to annotate on this and see if I can explain to you what I mean. Let's choose a color. Hopefully this will show up. Okay. So if you'll notice, A remains constant here, but B is doubling. Bear with me here because I'm going to write like a kindergartner there. B is doubling. And then you ask yourself, what's happening to the rate? If I double B, we know that because B is the only thing that's changing between those 2 trials, if you double B, we'll know how the rate changes. You'll notice that the rate is doubling. Okay, and that indicates that it's a first order reaction with respect to B. Okay, because if the rate is doubling, then if the concentration of B is doubling, then the rate is increasing by 2 to the first power. So let's see here. If I'm going to write this as a rate law, I know I'm going to take this off screen share for just a moment here so you can see. So I know that for my reaction A plus B going to products, I'm going to have some rate law expression that's rate equals K times the concentration of A to some power times the concentration of B to some power. Now, I just figured out by analyzing that data that this power for B is 1, because when I double B, the rate doubles, right? So if you double the reactant concentration and the rate doubles, that's indicative of a first order reaction. If you triple the concentration of B and the rate triples, that's a first order reaction. Quadruple the concentration of B and the rate quadruples, that's a first order reaction. In other words, when the concentration and the rate go up by the same magnitude, that's indicative of a first order reaction with respect to that reactant, okay? All right, let's go back and see if we can figure out this order with respect to A. So now we've got to choose two trials where B is held constant and A changes, right? Because now I want A to be the variable. So let's do that. Okay, if I choose experiments 1 and 3, you'll notice that B stays constant from 1 to 3, and A is going to double. And then if you analyze what happens to that rate as we go from 1 to 3, oh, well, it's also doubling or going up by the same factor 2 to the first power. Okay, and so again, that would indicate that the order with respect to A is also 1. Okay, so the order with respect to A is 1, the order with respect to reactant B is 1, and then we can say the overall order is just adding the two together. 1 plus 1 is 2. So the overall reaction order is 2. Okay. Let's try the other example Mr. Anderson did that was